By comparing live data against the stored database of waveform signatures, these synthetic systems can learn to recognize new patterns, adjust to environmental noise, and even predict future states based on the detected waveform trend. The relationship between waveform detection and environmental sensing leads to the idea of clandestine waves. These are waves that carry hidden, indirect, or encrypted information. Clandestine waves are often below the threshold of conscious detection, but still carry meaningful data in their shape and behavior. The concept can be expanded to cover sub-threshold waveforms in neural circuits, ultrasonic vibrations in sensor arrays, or minute chemical-induced oscillations in biological systems. These signals are not overt or obvious, but require advanced detection and interpretation tools to reveal the hidden order beneath the surface. By modulating these faint signals into sine waves and interpreting their frequency domain representation, a hidden layer of reality becomes visible. A key to interpreting these clandestine waves lies in pattern recognition and comparative waveform analysis. Once a base signal is identified and categorized, deviations from this pattern can be flagged for further investigation. Whether detecting the earlier stages of a disease or a trace plume from a leaking chemical tank, these deviations often serve as early warnings. The elegance of the sine wave allows for subtle fluctuations to be measured with precision, especially when high-resolution analog to digital converters and signal processing algorithms are used. To understand how these signals are measured in the field, consider how drones, satellites, and wearable health devices use arrays or sensors to scan the environment. Each sensor is tuned to respond to specific frequencies or chemical interactions. The signals they collect are processed in real time using onboard processors or cloud-based systems that reconstruct the waveform into interpretable data. The result is a sine wave pattern that represents the presence, strength, and dynamic behavior of the targeted chemical or biomarker. This allows not only the identification of what is being detected, but also provides insight into how it spreads. Change perspective, the frequency at which sensors must be modulated to detect such subtle interactions depends on the properties of the target compound. Lower frequencies are often used for large molecules in biomolecular biomolecules due to their slower interaction kinetics. In contrast, higher frequencies are necessary for small gas molecules or volatile compounds that change rapidly. Choosing the correct frequency range is essential to produce a clean, detectable sine wave and avoid interference from background noise. Ultimately, the transformation of environmental or biological signals into sine waves offers a consistent, elegant method for interpreting the complex data surrounding us. These waves allow the integration of sensor technology with biological principles, creating a bridge between the inner and outer worlds. By understanding how these signals are modulated and processed, researchers and engineers are building more advanced systems capable of early detection, rapid response, and intelligent adaptation adaptation to changing inputs. As we continue to uncover the layered signals hidden within natural systems, the humble sine wave becomes a powerful tool, not only for scientific analysis, but also for navigating the unseen architecture of reality. Whether in the brain's cerebellar structure, the electrochemical modulation of neuromodulators, or the oscillatory response of a chemical detector, waveforms serve as a fundamental expression of change, continuity, and interpretation. This deep relationship between wave, frequency, and information will continue to guide our understanding from cognition to climate, medicine to mechanics, biology to information theory. Freeman Dyson and Freeman Dyson's ideas about advanced civilizations constructing vast energy harvesting structures around stars inspired not only science fiction, but also real scientific efforts to search for signs of such astro-engineering projects in the cosmos. Modern astronomical surveys have incorporated elements of Dyson's thought experiment into their search strategies, particularly in the field known as the search for extraterrestrial intelligence. This has led to studies that aim to detect the kind of telltale infrared signatures Dyson predicted, using increasingly sophisticated telescopes and data analysis techniques. The core idea Dyson proposed was that a civilization building a sphere or swarm to capture most or all of its star's light would necessarily have to dispose of the collection energy somehow. According to the law of thermodynamics, this energy would eventually be reemitted as heat, most likely as infrared radiation. From a great distance, such a star would appear dim or even invisible in invisible light, while shining brightly in the infrared portion of the spectrum. Modern surveys have tried to detect such anomalies by searching for stars or entire galaxies that radiate more heat than expected for their visible brightness. One of the earliest large-scale efforts inspired by Dyson's idea was conducted by researchers using data from the infrared astronomical satellite, which operated in the 1980s. Scientists examined data from tens of thousands of stars, looking for sources with unusual infrared emissions that could not easily be explained by natural astrophysical processes, such as dust clouds or the aftermath of stellar birth and death. While these studies identified some objects with excess infrared radiation, natural explanations always fit the data more convincingly than artificial ones. In the modern era, surveys using more advanced instruments like the Wide Field Infrared Survey Explorer have extended this work. Astronomers have scanned millions of stars and galaxies in search of the kind of infrared excess that could signal large-scale astroengineering. In 2015, for example, a group led by Jason Wright at Pennsylvania State University published a study that analyzed data on hundreds of thousands of galaxies, searching for cases where the infrared output suggested significant energy reprocessing by something other than stars or dust. The study found no definitive evidence of galaxies radiating energy in a way consistent with massive artificial structures like Dyson spheres. However, it did identify some candidates worthy of further study, where the source of the infrared emission is not entirely understood. In addition to looking at entire galaxies, astronomers have applied Dyson's logic to individual stars. One of the most famous cases that drew attention in recent years was the star known as KIC 8462852, often nicknamed Tabby's star. This star exhibited strange and irregular dimming patterns detected by the Kepler Space Telescope. Although the primary hypothesis for these dimming events focused on natural phenomena like clouds or dust or debris from shattered comets, the unusual signal of the light curve led some to speculate, at least initially, that it could be evidence of a partial Dyson swarm or other large artificial structure orbiting the star. Follow-up observations, particularly in the infrared, showed no excess waste heat.